Chapter 6, Bending Composite Sections. In this example, we do have a reinforced concrete beam with below dimensions, subjected to a bending moment of M is equal to 60 kilopound feet, and we want to determine in part A stress in concrete and also in compressive stress in concrete part and also a tensile stress in steel rebar. So we do have a 60 kilopounds bending moment applied to this section. Mhm. The dimensions are 12 inch in width and 18 in height, and rebars located 2 inch from the below bottom of the section. We want to calculate the stress in each part of this composite section. At the same time, we do know a elasticity modulus of steel is equal to 29,000 ksi, and a modulus of elasticity for concrete is 3600 ksi. The solution is the total area of steel first should be transformed into equivalent of area of concrete. So we convert the area of these two rebars of 1 inch diameter bars, steel bars, to equivalent area of concrete first. And for doing so, we first need the conversion of a factor of the modulus of elasticity of higher modulus of elasticity material to the lower one, which is a steel to concrete, which is 29,000 over 3,600, and that's equal to 8.05. That's the ratio of these two, and area of steel is equal to 2 of pi r squared, and that's 2 times pi times the diameter is 1 inch, so the radius is zero point 0.5 inch squared. That's a 1 point almost 57 inches square for the total area of steel. Then we have to convert it to the equivalent area of concrete. To doing so, it just gives us N, which is the ratio of those two modulus of elasticity times the area of the two rebars, and that's 8.05 from the top, N times the area of the two steel rods, which gives us A prime is equal to 12.65 inches squared. So it just simply says if we want to convert these two a steel rods to the equivalent area, as you can see here at the bottom of the section, that's A prime, that's N times AS. So the whole area is a unified and all is concrete. The actual one is we need to subtract these two, so that's the real one is n minus 1 times as, because the effect of the hole after cutting off these two rebars from the concrete should be subtracted from n, but we for our problem we just go with the simple one, which is n times as. But just in case in concrete design section, in structural analysis, or concrete structures design, this is the accurate one, just in case. So the next step is a calculation of the location of neutral axis. We do need to have our centroid to be lied at a neutral axis, and that's the finding the location of neutral axis. If we consider the neutral axis is h prime from the top, that's 12 inches width times h prime times h over 2 for the top section centroid, mm, minus the equivalent area of a steel, that's 12.56 inches times 16, from the top to the center of rebars, minus h prime, which is this distance, should be equal to each other. and that gives us a second degree equation based off h prime, and if you solve it for the positive root, it just gives us h prime is equal to 485 inches, 4.85. So that's h prime from the top. And that's the location of our neutral axis from the top of the section. So as soon as we have the h prime, we can easily calculate the moment of inertia, and that goes for two sections. The top one is for the concrete part at the top of the neutral line, and the one here in green is related to a prime, which is the equivalent area of steel rods. So that's 12, half of 12 times 485 cubed, because we are cutting it through here, the centroid, plus a 12 times 485, and that's AD squared. So that's a 112 base cube height plus AD2. And I think that should go like this. Let's modify it here. That's 112 plus AD squared. So that's 112 base cube height plus AD squared, because that is moving from centroid to other axis. That's a positive, and plus then AD squared, because I prime for a steel rod is almost negligible, and that's just AD squared. That's A, then D squared, which is distance from here to here. And it just gives us A prime is I is equal to the moment of inertia. If you do the math, it just gives you a moment of inertia is equal to 29 inch to the power of force. And for calculating of stresses, normal stresses is a, just go for example for the top part, for the sigma concrete maximum applies at the top of the section, which you can see the arrows. That's sigma maximum, which has the maximum distance from the neutral line, and that's mc over I based off bending formula. We have a 60 kilopound feet a moment converted to inches, 12 inch per feet times distance 4.85 inches over moment of inertia of the whole section, which is 29 inch to the force, and that gives us a sigma compression or concrete maximum is 1.72 kilopound square inches. And if you do the math for the steel rods, that's a sigma steel at the bottom of the section for each of them. That's N, again, the ratio of the two modulus of elasticity times My is again distance, which is 16 minus 485, which is this distance, over the same moment of inertia for the entire cross section, which gives us a 31.9 kilopound square inches for each of those steel rods. We'll solve more problem, and if we want to show them graphically, it just show us a 1.72 for the compressive concrete at the distance of 4.85 inches from neutral line, and each of the rebars has 31.9 ksi, and that's a tensile stress for rebars. Thank you. We'll solve more problem related to bending and composite section. Thank you.